right, so we're gonna talk about Newton's method, and actually what it does for Newton's method is this approximates zeros for us, is what this does. Which we know about 8 bajillion ways to find out zeros. You know, like finding out where the graph basically crosses this line right here. Newton had kind of an interesting way to go about it, which I thought was kind of cool. But I'll show you how it works in a sec. But we have setting an equation equal to 0. We have so many options for how to solve it. We could factor it. You could use the quadratic formula, depending on the function, of course. You could just solve for x, isolate the x. You could let's see, the rational zero test. We did that with the big mess of stuff. What other ways do you do that? Why is there a sign on my ceiling? What does that even say? What? Nullable. See what happens when you're gone? Is it really up there? Dumb stuff.
I don't think that's our fault.
I'm not saying it's yours. I mean, there's. Yeah. Anyway, so there's lots of ways. There's lots of ways to approximate zeros. Newton had a different way to go about it. He said something like this. He said, if I have some graph, let's say I've got some graph that goes like this. Who knows exactly what it looks like? But I want to find out where this zero is. That's what I'm trying to search for. I'm trying to find out where this graph crosses. And obviously, see, it looks like it crosses. But what he did is he took a point and he guessed. He just picked a point out there. It didn't really matter too much. And he said, all right, if I pick that point right there, what I want to do is I want to draw a line, a tangent line, that goes right through that point, like so. And I'm going to say wherever that tangent line hit, that point right there is going to be the zero of the function. Now, the problem is that's a little bit off, right? And it's totally based on guessing and whatnot. So what he did is said, all right, well, once I get this first guess right here, I'm just going to take that and plug it into the function and draw my tangent line for this. Okay, so I'll draw my tangent line for this guy now. And then I'll say that's my guess. So then I have a guess right there. And he said, well, maybe I'm getting a little closer there. So then he takes that point right there and then finds the tangent line for that. So he goes back up to, like, let's say here. And he has this tangent line right here. And he gets a little closer. And he gets this one. He gets a little closer. Anyway, so kind of a narrowed down method, and the picture gets kind of nasty. But what it is just a bunch of tangent lines. And wherever that tangent line hits, that's where it's going to go. Now, you don't have to know too much of that picture as far as how he calculated this. How he calculated is he said, if I wanted to find a zero, and he did x sub n plus 1, so he said, the next x is my guess. He was all about guessing. You pick a number, and then pick the next number in line using the number that he had. Kind of like a recursive function. I don't know if you guys remember recursive. It was the sucky one where you needed the one before it to get the next one. It was always kind of tough to plug back. Anyways, so this is actually a recursive function, so it's a little tough to do. But it says if I want to find some x value, I'm going to take the x value that I guessed, x sub n, and I'm going to subtract the function at that value, divided by the derivative of the function at that value. This pen's dead. Change colors, maybe black is. Okay, so it basically said I'm going to pick some value, right? This value that I want to get right here, I'm going to pick some starting x value. I'm going to plug it in right here, whatever the value is. Take away the f of x, so some function value, divided by the derivative of that function. Okay, so we want to try to do this process, and this process is going to happen over and over again. And the more you do it, the more accurate this is going to get, and we're going to be pretty good. Okay. It stands for the next number in the sequence. So if this is some n value, this is the next number in that sequence. So if I want the next number, I take the number before it and plug it into that function right there, which is recursive. We've done that a little bit before. It was probably in pre-calculus that we did that. That we did recursives. Yeah. Remember doing arithmetic and geometric sequences and all that stuff? All right, let's go ahead and take a look at a pretty simple function, and hopefully this will work out for us. Let's say we had x to the second minus 2. And I want to find the zeros of this function if I can. I'm going to use Newton's method, although we probably have a lot better method for this one is my guess, just maybe. But starting out with something easy that we can see the answer to. Like, what would the zeros be for this one? Square root of 2, right? So 1.414. You guys all okay with that? Because we're finding out where this function would equal 0. So you'd move the 2 over and square root, and so you would get the square root of 2. Okay? So the square root of 2 is going to be our function for this. What I want to do is I want to just, we could graph this. Let's graph this graph and see what it looks like. Although you guys don't need that. What's it look like? It's parabola down 2, right? Okay, so that's what the graph looks like. Now let's just look at one of them. There's obviously 2 zeros here, but let's just look at one of them. Let's try to find out where this 0 is right there. We all know it's the square root of 2, but I want to use Newton's method to find out exactly where that point is. Okay, so we're going to guess. Now for our first guess, let's say that we're going to guess x equals 1. Okay, let's say x equals 1 is my first guess. Now I don't know exactly where x equals 1 is. I could find it though. If I plug in a 1 right there, what do I get? 1, so a bit of a negative 1. So 1, negative 1. Ooh, my graph's a little off. Sorry, guys. There. That looks a little better. So I'm going to guess this point right here is my first guess. It's my first point. If I draw a tangent line to that, right? I mean, you don't have to do this. It's a bit overkill. Tangent line should give me that value right there if I want the tangent line of that. Okay? But I'm going to use this Newton's method, which says take the n plus 1 that I want to find, take some x value, and take off the function at that value, and divide it by the derivative at that value. Okay? So that's what I'm searching for. So let's say I want to find what I think is my first approximation for the 0. What I'm going to do is I'm going to plug a 1 in for all those x sub n's. Okay, so to find my next number in line, whatever this x sub n plus 1 is, I want to plug a 1 in for all those x values right there. So it's going to be a 1 minus the function at 1 divided by the derivative of the function at 1.
Could x be like anything?
X can be any number that you want. Okay, now there's a couple of small restrictions, and I'll show you the pitfalls in a moment, but for now I just want to do a couple of these. But they call these iterations. Basically, every time you do one of these, they call it an iteration. So we want to do like 4 or 5 or however many we want to do until we think it's pretty accurate. Okay. All right. So I want to take 1 and I want to subtract out the function value divided by the derivative of the function value. So that means I need to find the derivative real quick here. So the derivative, which is pretty easy on this one, is going to be a 2x. Okay, that's the derivative. And so for this value, I'm going to go 1 subtract the f of 1. Let's see if I plug a 1 in right there. Let's see, what do you get? Negative 1 over the 1 plugged in here, which is 2. Okay, so I've got 1 plus 1/2, so I get 1.5. Okay, so my x sub n plus 1, plus 1 equals 1.5. So we're saying now that 1.5 is our 0. That's our new guess now. Okay, so now we're going to do that exact same thing again. And now we're going to use 1.5 for our guess. Okay, now as far as the graph goes, 1.5 was this number right out here. And then I go right up to the graph right here. And then I want to find the tangent line of this guy. And that's going to get me closer and closer as I go. Okay, so now what I want to do is I want to plug in 1.5. So if I want to find my next value, my next term in this sequence, I'm going to go 1.5 minus f of 1.5. And then divided by f prime of 1.5. Okay, so I want to figure out what all these are going to be. So 1.5, take off, let's see, f of 1.5. So I want to plug in a 1.5 into my function. Okay, so I got to take, what is that, 2.25, I think? Minus 2, so 0.25. Divided by f prime of 1.5. So if I plug that in the derivative, 1/2, doubles 3. So I get 3. So I get 1.5 minus 0.25 over 3, which equals, somebody already have that. What'd you guys get? Nothing yet? Okay, I got it. 1.5 minus 0.25 divided by 3.
17.
Oh, you guys have got it. Oh, let's do decimal. 1.4166667. Say again?
17.
17 twelfths? Okay, sure. Can I make that?
Yeah.
Okay, sure. 17 twelfths is fine. You can leave a decimal fraction. Besides, I'm going to show you a nice little shortcut here in a second, so don't worry too much. Okay, so now I got 1.4166667 repeating, right, basically, so I got that nice little pretty fraction. Now I want to do that again, right? You want to keep going as far as you want to go until you feel pretty satisfied with what the answer is. Okay, so we would go again, and we go xn plus 1, and this is going to equal 1.4116 repeating, and then minus, let's see, you're going to go f of 1.416. Everybody ready for the shortcut yet?
Yeah.
Okay, good. I'm glad we're all on the same page here. Okay, so let's say I plug that in again, right? And I find out what my new value is. What number is this getting closer to, by the way? Just curious. 1.41. Wasn't the square root of 2 to 0? Right? What's the square root of 2 equal? Decimal wise. 1.414, blah, 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 right? So it's getting, the more iterations I do, the closer that's going to get to actually getting square root of 2. And I can go as accurate as I want. They might say, hey, go within 0.0001 accuracy, okay? So you want to figure out what, anyway, I'll show you how to look at that. Okay, now, the shortcut for doing this, because obviously we don't want to have to be plugging in a bunch of values. We have these very powerful calculators. Let's use them, okay? So let's go ahead and set it up a little something like this. Screen's getting weird. Okay, clear all your stuff out there and get it to a nice little window that we can. First off, let's graph the original function. That's x squared minus 2. Okay, so we're going to go x squared minus 2. So that's our parabola, which we kind of knew what it looked like anyways. Okay, now what I want to do is put in the derivative. So go back to your y equals, go to your second equation and go 2x. There's your derivative. Okay, so there's that. And just by looking at those, you're like, well, that didn't help me at all, because it really didn't. So what we're going to do is we're going to type in this equation right here. We're going to type in this Newton's method. We want to get that in there if we can. Okay, so what I'm going to do is I'm going to go back to my y equals. I'm going to turn these guys off, because I don't really need those on. And I'm going to go to my y3, and I'm going to say I want some x value. Because I just went over to the equal sign, and see how the equal signs aren't on anymore.
Oh, yes.
It makes it so if I turn, like, let's say I didn't want that one, right? I just want the highlighted one. It only graphs the one. It doesn't. It just. But you can keep it in the calculator as stored. Okay. So I would just turn those off. Just go hover on the equal sign, hit enter, and then that'll either select or deselect. Okay. Now what I want to do is because I don't need all those graphs, right? I don't need a ton of graphs on there. Plus, then I have to switch between. Don't want to mess with that. Okay. So what I'm going to do is I'm going to type in an x value, which we have this funny button that looks like an x. X minus f of x. Now this f of x is our original function, which is y1, right? So what I want to do is I want to throw y1 in there if I can. So I'm going to go subtract y1. Now to get there, you can go to this VARS button, the variables button. Okay, go to your variables button. Notice on the right there, on the top right, it says y variables. Okay, so if I scroll over to y variables, first one on there is function, which is my y equals, and I can select y1. Okay, so I'm going to go x minus y1. Divided by y2, right? So if I take my function and divide it by the derivative of that function, right, which is y2, that'll give me my little Newton's method, okay? So I've got, to get back to the y, I hit the variable button. This guy right here. Variables button's right here. VARS. Okay, scroll over to the y variables. And number one on there is function. Okay, so I'm going to go to function. This time I want y2, so I'm just going to go to y2. And now I've got that's my Newton's method right there. It says take an x value, take off the function, divided by the derivative of the function.
So y2 is the derivative of the function?
So y2 is my derivative. Yep, y2 is the derivative. And I can label them as whatever I want, but I stole y1 and y2 as in those guys right there.
What is so y3 would be like the second derivative?
Y3 would be the Newton's method generator. It would be the zero generator for you. That's what that would be. So there's not really a name.
Y2 is the derivative.
Y2 is the derivative, yeah. Y1 is the original function. So I got x minus y1 over y2. Now you could type in all that stuff, which is fine. There's nothing really wrong with doing that. It's kind of cleaner that way, I think. But anyways, so now I want to just generate a couple x values. Okay, if I go to my graph now, which is kind of like a gross, weird-looking graph. But let's say I start at x equals 1, just like I did before, right? That was my iteration right here. That's what I wanted to start at. I just go second calculate value, and I want to type in a 1. Okay, well, I get 1.5, which we already got that from before, right? Now I want to plug in 1.5. Well, I'm already in my value system, so I can just go 1.5, and that's my second guess. Okay, that's my new guess. Now I get 1.4166667, right? So I'm going to type that in from a new value. So 1.4166667. And I get 1.412157. Okay, so I'm going to type that in now. 2157. Oops. Yeah, 1.4142151. Did I skip a 4 last time?
Yeah.
I think I did. So let me go back. 1.414, and then what I said was 2157. Cool. So I get 1.4142136. So I'm getting pretty close. Okay. Now I'm going to type in that value as my next guess. And I can go as many times as I want here. 1.4142136.
How do you know when you're done?
Well, watch what happens after a second here. Okay, what's my next value to plug in? 1.4142136, right? So 1.4142136. Well, my next value right? So I'm basically just plugging in the same number over and over and over again, right? And at some point, it's going to come down to if I get my 0 to within 1, 2, 3, 4, 5, 6, 7. 7, that'd be the 7th place of the decimal. I don't know if there's a name for that. Probably. Is that the millionth? No, that'd be the 10 millionth decimal place. That's pretty accurate, you know. So you just go until, and they might tell you, you know, when to stop. They might say get it within 0.0001 or something like that. So you just check your table and see how it differs, and then call it good. Okay. All right, cool. So that's what I would do. Use your calculator because it's going to help you out a ton as far as saving you time. Okay. All right. So let's look at one more real quick here, just to make sure we're okay with this. Is anybody dying to see the proof of this?
Oh no.
Stop. Because I can show it to you real quick. It's not too bad.
Well, it wasn't on the, he didn't do it on that document.
Okay, now as far as Newton's method go, the reason I like doing that y stuff, because on my calculator now, if I go back to my y equals, I can just replace my function and then my derivative of my function, y1 and y2, and I can just clear those out, and now I can just change, I can leave those as y1 and y2 in there, and then I always have that Newton's in there. So that helps a little bit, and I can just change my function, and then I don't have to type that in again, you know, save me a little time.
Okay, so on the test, is it gonna have us have to like? Because you said that part of it you can't do with your calculator.
Oh,
So are we gonna?
they won't give you a super hard one.
Okay.
Now they might give you like a 0 that lands on a good number, and so you might be able to get pretty close there. But usually this is the calculator version on this one. So, yep. So on this one, let's go ahead and type in our function. So our function is 2x to the third. So there's my function. Now I want to take the derivative of that function. So hopefully that's what, 6x squared and plus 2x minus 1. That's my y1, y2. I don't really want those graphs on there because, well, if I graphed them, first off, it'd be nasty. First off, it'd be kind of gross. I'll show you just what they look like. There's my original function, which I can kind of guess where my value is going to be. So I got all three of there on there, which is kind of gross first off. It's just I don't need all that big mess. Okay. The other thing is if I'm typing in values, because I need to build like a recursive type idea. If I were to build values, like say calculate value, and I type in, let's say I started at -1 or whatever, right? If I start at -1, first off, it tells me which y value that it's actually given me, which is on the first original equation. I can actually hit the down arrow, and it'll switch it to y2, and the down arrow will switch it to y3. So you can alternate between them, but that's just kind of more work than you need. It's easier just to go turn them off, okay? So what I do want to look at, though, is on my y equals, let's say I turn these guys off, here and here. So I just graphed the original function, and I want to see about where that 0 looks like. Looks like the 0 is about at -1, which I can just quickly check. Oops, -1. And so I get +1. So it doesn't look like -1 is the actual 0 for that. Now, go ahead and pick that to start. You can pick whatever you want really to start. There's only a couple little catches there. But we're going to pick, let's say we pick -1 for our first x value, okay? So let's say I pick x equals -1 for my first value. And I plug it into my little equation, plug it into Newton. So we'll put a little n right there. And I get a new resultant x value, okay? So I'm going to plug in x equals -1 into my Newton, okay? So if I go back to my y equals, turn this guy off, and turn this guy on, and graph it. I know, it's so slow. And then I can calculate value, and then -1. So -1 gives me -1.33, right? So -1.3 repeating, basically. Okay, so after I plug it through Newtons, that's what I get. Now, this is my new guess, okay? So I'm going to bring this down here. Now I'm going to go x equals a -1.3 repeating. I want to plug it into Newton. And then see what I get, okay? So I'm going to plug in -1.3 repeating. So I get x equals -1.243386, okay? So 1.243386, okay? So now I'm going to type that guy in. Okay, so I'm in my values here, so negative 1.243386, and I get, I better write this down here, negative 1.2486, plug it into Newton, and my new x value is negative 1.233855. You should see the table they want you guys to fill out for these.
No.
It's huge. They want you to do like each individual part of it, and like, jeez Louise. It's crazy. All right, so let's plug in this one. I think we're going to get pretty close. Remember, I'm trying to get it accurate within 0.0001, which means if I look at the fourth number after the decimal, so 1, 2, 3, 4, I want those numbers to all be the same up to that last number. If I can get it within that, I'm going to be pretty happy. Okay. So I'm going to plug this in. So it's a negative 1.233855, and I get x equals negative 1.233752. Okay, so we're actually within our margin of error here now, I think. We got 2338 and 2337, so those are within 0.0001 of each other. If you want to do one more just to be safe, you can, but that looks to be pretty darn close. Okay. All right, so we're feeling pretty good about that? Now, a quick way to check that, if you were to go back to your calculator real quick, just check to see if that is a 0. Okay, so if I went back to my y equals, turn my original on, turn my Newton guy off, and go back to my graph. And a couple ways to check this. First off, we can just type in the value. So we got negative 1.233752, and I get y equals negative 4 times e to the negative 7. So pretty much 0, right? In scientific notation. It's 6 zeros in there, so that's pretty small. You could also go to second calculate, and then number 2 on there is 0. So you can go to number 2, get on the left side, get on the right side, and then guess. Now that we've done this, why do you think they want you to guess? No. They always ask us to guess, right? What do you think your calculator is doing in the background to calculate these zeros? It's method. It's doing guess and check with Newton's method. So they're asking you to guess because they want you to guess a first value so that they can do less iterations. That's lazy. So your calculator is trying to not get bogged down, and so it's asking you to guess. That's why it's asking you to guess. Okay? And in the past, it's always not mattered. So why guess? Who cares, right? It's because that's the programmers in the calculator were like, well, let's see. If we don't want to get this bogged down, let's have them, make a number that's close. At least do less iterations. But anyways, so we get guess. I don't need to guess. So we get negative 1.233752. So pretty darn close to the 0 that we just got right there. Okay. That's what we just did. Fine. Okay, so you guys get the idea? It's not too bad. Newton's is okay. It kind of seemed nasty at first, right? But it's really not too bad once you kind of get the hang of it. One last one real quick here. A couple little pitfalls. Yeah, there's always a couple little pitfalls, aren't there? And it's kind of a trick question.
Is that a 1/3?
No?
They're confused.
Fixed to the 113.
Oh, yeah, the 1/3? Yeah.
Okay.
Oh, you need me to write that better?
Yes.
Just
Oh, okay.
Is that better? Sorry. That's who put that there. Makes sense now. Okay, now Newton's is a bit overkill for this. Besides, Newton backfires, right? Go ahead and test out Newton here and see what happens. Okay? A couple little pitfalls for Newton. Sorry, so let's go ahead and type these in. Well, yeah, we're doing a lot of work for the answer being pretty obvious, right? What's the 0 for this one?
0.
0. Okay, so we already know what the answer is, right? But Newton actually fails on this one. And I'll tell you what. I know. It fails for a couple reasons, but we're going to keep it pretty simple. But x to the 1/3, go ahead and take the derivative of that, which would be, what, 1/3?
Oh, you can't.
And then x to the negative 2/3 power. Okay. Now, I don't really care to have those on there. Right? Need this one though. Okay, and scrap.
For the big one.
Yeah, it certainly doesn't like this one, does it? Interesting. Okay, so let's say we were to guess, right? Well, first off, yeah, you could second calculate guess. Oh, okay, 0, sure. Guess 0, and we get, y is nothing. So now where do I plug in? I don't even know. So I know I want it to be 0, so let's get close to 0. Like, how about 0.1? Okay, so let's plug in 0.1, and we get negative 0.2. Okay, so that would be my next guess, is negative 0.2, right? So I plug in a negative 0.2, and I get 0.4. Okay, that'd be my next guess. So let's type in 0.4. Okay, negative 0.8. That'd be my next guess. Okay, so negative 0.8. 1.6.
What do you say next one? Negative 3.2.
Yep.
I wonder what the next one is. Positive. I see it. Okay, anyways, is that getting closer and closer to any specific number? No. So they have this fancy word for that. It's called diverge. We'll get to that a lot later. The ones that we were doing, these guys right here, this sequence, it's a recursive sequence. It converges to a specific number, like square root of 2 or like negative 1.2 or whatever it happens to be. This one diverges. This one gets bigger and bigger and bigger. It doesn't go to a specific number. Okay. So this one actually Newton's method fails, and it's just the way that it goes. The reason is the first derivative is not differentiable at 0. That's really the big problem. Okay, that's the big. Okay, the other big issue, the other big problem, and not on this graph, but let's say I had a graph that looks something like this. Let's say I go from concave concave down, and then I switch to concave up, like so. Let's say we're looking at that point right there. That point's an inflection point, okay, which we've talked about. What's the slope of that point right there? 0, right? This would be the tangent line, which is kind of weird. The slope would be 0. So if I were to plug that into my Newton's method, right, it would be x minus f of x divided by f prime of x, right? What's wrong with Newton's method on this guy? Undefined. Yeah, undefined, right? So if it start out with this value, that's bad, okay? So you don't want to start out where you have an inflection point, okay? So as far as picking values, you can pick whatever values you want, but I wouldn't pick an inflection point where it switches. I would pick one, right around it or whatnot. And that's because it's going to backfire right there. And then you have to watch out every once in a while you get something that backfired. If the derivative is not differentiable across the entire thing, sometimes you run into problems there too. So just a heads up, just to watch out, but those are pretty simple to work with. So, all right, cool. That's all we got for today. So we are on 233. I promise I will answer an abundance of questions if you need them on block day. That'd be tomorrow. As far as like the